NASA's annual budget sits at $25 billion. ISRO operates on just $1.5 billion, less than 6%. In fact, a single launch of NASA's flagship moon rocket cost $4.1 billion, nearly 3 times ISRO's entire annual budget. NASA has the capital, the world's heaviest operational rocket, and multi-billion-dollar deals with giants like SpaceX, Blue Origin, and Lockheed Martin. So when news broke at the civil space meeting last week in Bengaluru that NASA formally invited ISRO to join its permanent moon-based project, global media called it a friendly diplomatic gesture. Diplomacy is certainly a factor, but as a complete explanation, no. Why would the richest space agency on Earth, with 50 years of deep space dominance, ask a foreign agency to help build the central infrastructure of its most critical mission? The short answer, it's not just a moon mission. It's also about de-risking one of the most ambitious infrastructure projects in the history of space exploration. To understand the hardware problem, you have to look at how Western aerospace operates versus ISRO's structural design choices. For the past 5 years, NASA's primary mechanism for delivering uncrewed equipment to the moon has been the Commercial Lunar Payload Services Framework, or CLPS. The idea was simple: buy payload space on private American landers built by startups like Intuitive Machines or Astrobotic. But the reality has been brutally expensive and technically volatile. Astrobotic's Peregrine lander suffered a propellant leak hours after launch and burned up in Earth's atmosphere. Intuitive Machines' Odysseus landed, but tipped over on its side upon touchdown due to sensor failures. Each of these missions cost between $100 and $200 million just to deliver less than 100 kilograms of functional, scientific payload. Under current Western commercial launch architectures, delivering just 1 single kilogram of payload to the lunar surface costs between $1.2 million and $1.5 million. In those economics, scaling a permanent lunar presence becomes an enormous challenge. Now compare that to the engineering stack ISRO deployed during Chandrayaan-3. ISRO achieved a soft landing on the lunar south pole for approximately $75 million, less than the budget of a mid-tier Hollywood film. But the critical metric isn't just the low price tag, it's the failure-tolerant architecture. Because ISRO operates under tighter budget constraints, its missions are often designed around efficiency, redundancy, and risk management. Chandrayaan-3 was built specifically to demonstrate a safe and soft lunar landing, using multiple sensors and autonomous landing technologies to handle the uncertainties of the lunar surface. This is where the moon-based synergy emerges. A permanent base at the lunar south pole needs a massive volume of uncrewed, reliable, low-cost utility hardware. Solar and nuclear power microgrids to survive 14-day lunar nights where temperatures drop to minus 130 degrees Celsius. Autonomous excavation units to scrape and process lunar regolith for trapped water ice. Surface communications nodes to create a local mesh network across rugged crater terrain. A permanent base will need exactly this kind of reliable, repeatable infrastructure at scale. And NASA's own moon-based strategy is already built around commercial and international partners contributing technologies and infrastructure. That creates a potential opening for India and eventually Indian space companies to contribute to that supply chain. It's not an act of charity. It is a cost decoupling strategy designed to outbuild China's competing lunar base without exhausting the US budget. Hardware is only half the equation. You cannot build a moon base without answering one primary question: where's the water? This single question explains the global obsession with the lunar South Pole. The South Pole is home to permanently shadowed regions, deep craters that receive little or no direct sunlight. These extremely cold environments are believed to contain deposits of water ice. In space exploration, water isn't just for drinking. Split water into hydrogen and oxygen, and you get breathable air and liquid rocket fuel. Finding that ice is the difference between a self-sustaining lunar base and an unsustainable money pit. But there's a massive technological problem because these craters are in absolute total darkness. Standard optical cameras are completely blind. To see beneath the soil in pitch darkness, you need synthetic aperture radar, SAR, and that builds us directly to the active software engine operating between NASA and ISRO, NISAR. At $1.5 billion, NISAR, the NASA-ISRO synthetic aperture radar, is the most expensive Earth observation satellite ever built. But its technical architecture offers a glimpse into how NASA and ISRO could approach some of the mapping challenges they'll face on the moon. NISAR is the world's first satellite to operate a dual-frequency radar system simultaneously. NASA's L-band SAR operates at a 24-centimeter wavelength built for deep penetration that cuts through surface layers down to solid bedrock. ISRO's S-band SAR operates at a 9 cm wavelength, optimized for high-resolution surface roughness, soil moisture, and fine structural detail. When you stack L-band and S-band radar data together, the software can differentiate between pure surface dust, shallow rock, and actual subsurface ice deposits buried meters beneath the soil. The public data pipeline currently running between NASA's ASF-DAAC portal and ISRO's Bhu platform isn't just an Earth monitoring system. The calibration algorithms, signal processing engines, and dual-band data stacks built for NISAR are a potentially valuable technical foundation for mapping the dark craters of the lunar South Pole. Before humans construct habitats on the lunar surface, autonomous orbital probes equipped with this exact dual-band SAR setup will scan the terrain. The processing engine currently crunching NISAR's terabytes of data is the kind of technology that could eventually help identify and characterize resources such as water ice for future lunar infrastructure. Solving the hardware costs and radar mapping solves the engineering. But historically, American space collaboration with foreign nations has hit a massive legal brick wall. ITAR, the International Traffic in Arms Regulations. For decades, ITAR classified top-tier space technology, launch software, and advanced sensor components as defense articles. Under strict ITAR rules, sharing technical schematics or co-manufacturing flight hardware with a foreign space agency required years of State Department approvals and mountains of red tape. This legal friction is precisely why US aerospace supply chains remain locked inside expensive, traditional domestic defense contractors. So how do NASA and ISRO legally co-develop lunar-based infrastructure without triggering ITAR violations? Enter Trust, transforming the relationship utilizing strategic technology initiative spun out of the broader US-India ICET framework. Now, trust is not a generic diplomatic pledge. It is a targeted regulatory workaround designed specifically to streamline defense and space tech transfers between Washington and New Delhi. By establishing pre-cleared industrial corridors, trust allows Indian private space startups and defense suppliers to integrate directly into NASA's commercial supply chain, bypassing years of standard ITAR clearance hurdles. And the timing of this legal clearance is not an accident. It is driven by raw geopolitical urgency. While Western media focuses on Artemis, a parallel space race is unfolding at the lunar South Pole. China and Russia are actively building their own alliance, the ILRS or International Lunar Research Station. Beijing has already signed up over a dozen international partners offering state-subsidized payloads, free launch infrastructure, and joint lunar base access to global South nations across Asia, Africa, and South America. In this high-stakes lunar Cold War, the moon is being carved into two distinct operational blocks, the US-led Artemis Accords versus the China-led ILRS. NASA realizes that maintaining dominance requires more than technical capability. It requires scale, speed, and cost efficiency. By cutting through ITAR red tape and tying ISRO's deep industrial capacity directly to Artemis, Washington isn't just saving money. They're ensuring that the fundamental utility standards, communications protocols, and supply chains of the permanent moon base remain firmly anchored to the Western-aligned bloc. Now, most media outlets reported the civil space meeting as just another high-level handshake, but they missed the massive economic shift happening underneath. Today, 70 nations have signed the Artemis Accords, but look closer at where the actual hardware is coming from. When NASA builds hardware with traditional Western partners, it comes at G7 prices. The European Space Agency's service module for the Orion spacecraft costs over $1 billion per unit. Japan's JAXA pressurized lunar rover is budgeted at over $2 billion. Canada's Canadarm3 robotic system for the Lunar Gateway Station carries a $1.2 billion price tag. NASA simply cannot build a permanent multi-building lunar base if every utility node, rover, and power unit carries a $1 billion price tag. And that is why the NASA-ISRO invitation under the Trust Framework is a structural game changer. It shifts the relationship from political signing to deep tech industrial manufacturing. The global space economy is projected to hit $1.8 trillion by 2035. By integrating ISRO and Indian defense tech suppliers directly into Artemis supply chains, Washington is tapping into an industrial base that builds deep space hardware at 70% lower cost than traditional Western prime contractors. For Indian space startups, this completely rewrites the playbook. They're no longer competing for low-margin domestic tenders. They're being fast-tracked to build precision sensors, radiation-hardened electronics, and autonomous lunar rovers directly for the largest space program in human history. This isn't about ISRO helping NASA save a few $1,000,000. It is in fact the birth of a dual-nation commercial supply chain, combining America's heavy capital with India's extreme margin engineering to make a permanent moon base economically viable. Therefore, NASA's invitation to ISRO marks a fundamental turning point. The era of single-nation space dominance is officially over. So 4 structural shifts summarize this entire story. First, the economics. The legacy model of hyper-expensive single-use G7 hardware simply cannot scale for long-term presence. To sustain an operational base at the South Pole, NASA needs India's frugal engineering model, where algorithm-heavy, failure-tolerant software replaces billion-dollar hardware redundancies. Second, the infrastructure. Through the dual-frequency SAR software calibrated on NISAR, India joins Artemis as a core technology partner. ISRO brings the exact software and data stack needed to map, locate, and unlock the most valuable resource on the moon: subsurface water ice inside the dark craters. 3. The geopolitics. Under the trust framework, this agreement bypasses traditional ITAR red tape, fast-tracking India's commercial sector into the global deep space supply chain. And fourth, the real race. The race for the moon won't be won by giant state budgets alone, but by resilient, low-cost commercial industrial engines. NASA brings the heavy capital and heavy lift transport. ISRO brings extreme margin engineering and deep space mapping mastery. And together, they aren't just sending humans back to the moon. They're building the economic and operational blueprint for how humanity stays there. If you found this deep dive valuable, make sure to subscribe to Tech Brew with Vandana Nair. And I'll see you in the next one.